What's up, y'all? We are going to do trigonometric integrals today. This should not be confused with something called trigonometric integration, which is another kind of more complicated integral. But what I want you to do to start is two little warm-up anticipatory set problems here. Use some u sub to do both of these integrals. So I'd like you to hit pause, do the integrals. I'll pop the answers up in just a moment. Here they come. Okay, here you go. Hopefully, we agree here. We do a little u sub. U is cosine x for this one. Du is negative sine x. So really, I just rewrite this as a negative integral u to the fifth du. Gives me negative 1/6 u to the 6 plus c. And then I always make sure to rewrite it with the variable that was originally given to me as. So I write 1/6 cosine to the 6 of x plus a constant. This one, similar. There's just two different u pieces. U is sine, du is cosine. That's nice that we don't have to deal with the negative. So I get the integral of u squared. The du here is that, but I popped it over to this side. So cosine x dx gets replaced with du. But u to the second plus u to the eighth, 1/3 u cubed plus 1/9 u to the ninth plus a constant, which I will then go and write with the original variable, 1/3 sine cubed x plus 1/9 sine to the ninth of x plus a constant. So you may be like, all right, I can do that. And if you say that, then you can do what I'm about to teach you. There is only one tiny little piece that you have to know. I guess I should say what the types of problems that we're tackling here. We're going to learn how to do the integral of things like sine to the seventh of x dx. You notice there's no du like there is for this right here, right? You know, here I had cosine to the fifth of x, right? And then I had my sine there, right? So the sine was the du. This one is just that sine to the seventh, and it's missing a piece, right? For now, we're going to stick with ones where these are odd, and we'll get to the point where we can do ones that are even as well. So you can do this very easily. If you can do this, I just have to show you a small trick. So let's get into that right now. In order to do this, we need to go back to pretty much the most important trig identity that exists. I'm going to prove it for you right now because it's so important. But if this is a theta, and this is an opposite side, and this is adjacent side, and that's a hypotenuse, and I'm going to just use the letters O, A, and H, then we can, oh, and I should mention, this has to be a right angle there. We can use the Pythagorean theorem to say O squared plus A squared is H squared. Opposite, it's just a squared plus b squared is c squared, but applied to this right triangle, or this one with the trig pieces, whatever. Anyway, notice I can divide by h squared everywhere here, and then I can rewrite that. This is really O over h squared plus a over h squared, and then the right side is 1. And you may say, oh, snap. Snap. Sorry. Really, what's O over H? It's sine, and then I got to square it, of theta, plus what's this one? A over H cosine squared theta is equal to 1. And now this is true for anything where I've got the same input on the sine and the cosine all the way through, right? So if I had sine squared of 10 plus cosine squared of 10, it would be 1. If I had something like sine squared of 10 plus cosine squared of 20, it's not going to give me 1 because the inside of the sines and the cosines are not the same. This becomes super important and essential for doing problems like this. So let's just jump into an example. That sine to the seventh up there is a little bit more work than I want it to be. So we're going to start with one that is a little bit easier. Say I had the integral of sine cubed x dx. Notice I don't have a du there. I don't have like a cosine that I can use to integrate this to a sine to the fourth of x, 1/4 sine to the fourth of x plus c. So instead, I need a better technique. I need to create the du. Well, what I want you to see is that I could write this as the integral of sine x times sine squared x. And you may say, well, why would he do that? Well, this sign is going to become my du. Because, look, I know I have an equation that relates sine squared and cosine squared. So this right here is my sine squared. What I can do is take this formula and write it as sine squared, and I'm going to replace the thetas with x's because that's what I'm using here. Sine squared x is equal to 1 minus cosine squared x. And then what I can do is, see, I've got sine squared here, so that's this piece right here, 1 minus cosine squared, is going to replace that. I didn't write my dx, sorry. So this guy's going to replace that, and then I'm going to be able to integrate it using what we did above. So this is the integral of sine x times 1 minus cosine x, cosine squared x, parentheses, dx. Now, u is equal to cosine x, du is equal to sine x. There's really a dx there. I didn't write it above, but you should be okay with that at this point if this is what you're learning. So this is the integral of, the 1 stays the same. This cosine squared turns to a u squared, so 1 minus u squared du, and then the sine x dx gets replaced with the, this is a u, the sine x dx gets replaced with the du. So I get du. And then I get, what's the 1 integrate to? U plus, not plus, come on, minus 1/3 u cubed plus a constant. And then all I have to do is replace my u's with cosines. So what do I get? Cosine x minus 1/3 cosine x cubed, missed that for a moment, plus c. Bam. So what I didn't have a du anywhere, so I just created it. Let's do another one. Next one. All right, let's bump it up. Let's go the integral of cosine to the 5th of x dx. Algebraically, this takes a little bit more work, but it's still not that bad. Still totally doable by you. I fixed the 5. My 5's and s's always look the same. Sorry about that. Anyway, here we go. So I sort of just did this one up here without saying what I was doing. What I did up here was I had these sine cubes. I basically stole one of the sines to use as the du and then left the rest of them there and then subbed out the rest of them. So I'm going to do the same thing here. I'm going to steal one cosine. This is the integral of cosine x times cosine to the 4th of x dx. And now what I'm going to do is get rid of this. I'm going to turn this all into sines. And you may be like, well, your little formula up here had squareds, and this is to the 4th. Well, you should know that I can write this as the integral of cosine x times parentheses cosine squared x squared dx. That's totally the same thing as the one to the left there. And then I'm going to use my Pythagorean identity. Sine squared plus cosine squared is 1, so cosine squared x is equal to 1 minus sine squared x. This right here is going to replace that. So I'm going to get the integral of cosine x times 1 minus sine squared x, and be careful not to lose that other power right there, dx. Now I'm going to do my u sub. U is, in this case, it's this is my du. That's what I've been targeting the whole time. So that's my u. So u is sine x. Du is equal to cosine x. So what do I get when I sub this in? I get the integral, the integral, open parentheses, 1 minus u squared du. And that I can FOIL. If I FOIL this thing right here, actually, let's see. Yeah, so sometimes you can find like another substitution in here. But notice this is u squared, and I don't have a 2u out front, so I can't just integrate this using power rule. I need to FOIL it out. When I FOIL out this guy right here, I get the integral of 1 minus, there are 2u squareds, and then I get a double negative, u to the 4th du. And then that integrates to u minus 2/3 u cubed plus 1/5 u to the 5th plus a constant. And then my last step is simply to sub my u's back in. So now all those u's are going to change to sines. So what do I get? Sine x minus 2/3 sine cubed x plus 1/5 sine to the 5th of x plus a constant. Okay, let's do, hopefully this is making some sense, picking up what I'm putting down. Let's do one more. This one is going to be one where I don't have just a cosine or a sine. So let me write it because I'm going to run out of time. What is this one? We're going to do integral of sine squared x times cosine cubed x dx. Okay, this one. Notice this one is an even power. This one is odd. So going back up to here, remember I said I needed to create the du, right? And I need to have things that are evens left over because that's the only way I'm going to sub these things out appropriately using the Pythagorean identity. So I think you'll see this as you do more of them. But what I need to steal, if I steal a sine for a du, then I'm not going to be able to do this. So what I need to do is steal one of the cosines as a du. This is really the integral of sine squared x times cosine squared x times cosine x dx. Now, this cosine squared is going to get replaced. So I'm going to get the integral of sine squared x, open parentheses, 1 minus sine squared x times cosine x dx. And then I'm going to do my u's. U is sine x, du is cosine x dx. When I sub that in, I get the integral of, u squared, open parentheses, 1 minus u squared with a du. See, if I had tried to use the sine, I got to use the odd piece here. The key is with these is I need an odd piece. So I got to use that odd piece to create the du, and then mess with everything using the Pythagorean identity to get it down to something that is integratable. We'll learn later how to do it when they're evens. It's a little bit more complicated. So what do? I get the integral when I distribute this in. I get u squared minus u to the 4th du, which that gives me 1/3 u cubed minus 1/5 u to the 5th plus c, which gives me 1/3 u was sine cubed x plus, minus 1/5 sine to the 5th x plus a constant. Hopefully you see that these are not that bad to do the integral of, and you should be able to do some on your own.